So I want to finish off the proof of Sparse JL from last time, and then I'm going to analyze Fast JL, and then we're going to move on to some other, well, one application, and then move on to a new topic. So remember what Sparse JL matrix was from last time? It was this matrix pi. Okay, it's scaled by 1 over root s. Each column has exactly s non-zeros in random locations. Okay, those locations have random signs, and the rest of the column is 0. The columns are independent of each other. You could also use the count sketch matrix, as I mentioned last time. You'll see soon what that matrix, what the the random process that determines where the non-zeros go. You'll see what that needs to satisfy soon. Okay, we haven't actually finished the analysis yet for you to see where that becomes relevant. Remember that we wrote pi x L2 norm squared minus 1. That's the thing that we want to understand. We want a tail down for that. Right? That is a quadratic form, sigma transpose bx sigma, where bx is this matrix. Okay, so it's a block diagonal matrix. It has m blocks. M is the number of rows of pi. And each block has zeros on the diagonals. Okay? And on the off diagonals, we have xi, xj if both I and j are non-zero in row R. Okay? So that's that matrix. And then the Hansen-Wright inequality tells us, well, here, when I say p norm, I mean there's randomness over both sigma and delta. First, take the expectation over sigma. That's what Hansen-Wright lets you do. When you take the expectation over sigma, you'll get root p times the Frobenius norm plus p times the operator norm. But the operator norm and Frobenius norms are random because b is random. It depends on delta. So then you have to also take the p norms of those things with respect to delta. What we saw last time was, regardless of what delta is, the operator norm of b is never more than 1 over s. So for that, delta could have been a deterministic thing. Where we're going to actually use the fact that delta has some randomness in it is to deal with the Frobenius norm. Yeah.
In the argument about the operator norm of bx,
Yeah.
something you, towards the end, make the claim that, I forget which two matrices now, but two matrices both had, right, it was a difference of like positive definite matrices.
Yeah.
And then each of them had operator norm of most 1.
Yeah.
Could you just say why they each have operator norm of most 1?
Okay, you're asking why they, okay, so let me just go back to this operator norm of bx business. So you agree with me that the operator norm of bx is equal to 1 over s times the max over r from 1 to m, operator norm of well, I should call it bxr.
Yeah.
Okay, you agree with that? This is a block diagonal matrix. So now I just want to understand this thing. So now notice that bxr is equal to something like, I'll call it xr transpose.
Oh, the x's have unit norm.
Yeah, they have unit norm. Minus delta r1 x1 squared, delta r2 x2 squared, etc. delta rn xn squared. This is a diagonal matrix, and everything off diagonal is 0. Okay. Yeah, right. So, yeah. So then this implies that the operator norm of bxr is at most x. So xr is where you zero out things depending on what's non-zero in row r. So, well, the max of two things is less than or equal to the max of this, as well as the L infinity norm. Right, but these are both at most 1. And then there's a 1 over s that was out here. So. Okay, great. So now we're just left with the Frobenius norm. Okay. So let's write out what the Frobenius norm squared is. So the Frobenius norm, okay, that thingy is equal to, well, first of all, 1 over s squared. Right, there's a 1 over s that gets squared, times sum r from 1 to m sum over I not equal to j, because the diagonals are 0, I know, of delta Ri delta Rj xi squared xj squared. And rewriting this, let me write this as 1 over s squared sum I not equal to j xi squared xj squared sum r goes from 1 to m delta Ri delta Rj. And let me call this thingy here Qij. So what is Qij in words? Right? Qij is how many, so there's some, you can think of this matrix as being some kind of hashing thing, right? So there are n coordinates, and then there are m target, the target dimension is m. And each coordinate is getting hashed into s locations without replacement, right? So I is getting hashed to s locations without replacement. J is getting hashed to s locations without replacement. And what Qij is it's counting how many collisions were there. Okay? So that's a random variable that depends on delta, right? And this is where delta is relevant. This is why we need delta to be somewhat random. Okay? So let me write down a claim. So remember these values here. Okay. So if S is that, if M is that, and if P is that, the claim is that Qij P norm is at most P. Okay. So let's just pretend this claim is true, and let's finish the analysis of Sparse JL, and then we'll prove the claim. Okay. I mean, this is something you understand, right? It's, unfortunately, the deltas are not fully independent because they're exactly S per column. But if they had been fully independent, then this looks like a sum of independent random variables. You would use Chernoff or Bernstein or something. So this is standard. So let's pretend the claim is true. Let's finish the analysis. Now we want to bound the p norm of that thing. The p norm of, let's assume the claim. Okay, the p norm of that thingy okay, remember the definition of p norm. This is the expectation of that Frobenius norm to the p to the 1 over p. But that's the same thing as the expectation of the Frobenius norm squared to the p over 2 to the 2 over p to the 1/2. Okay, I'm just so this is a trick I guess I've used before in this class. So this is equal to, this p norm is equal to the p over 2 norm of the Frobenius norm squared to the 1/2, right? Which is at most the p norm to the 1/2. So let's look at this thingy. So this thing is equal to something to the 1/2. That 1 over s squared sum I not equal to j xi squared xj squared Qij p norm. Okay. And then now I can use the triangle inequality. This is, let me pull out that 1 over s squared square root. This is at most by triangle inequality sum over I not equal to j xi squared xj squared Qij p norm. But I said that this thing is at most p up to a constant, and there's a square root. So this is at most square root p over s sum I not equal to j xi squared xj squared 1/2, right? But this thing here is at most sum of xi squared squared, right? Which is 1. So this thing is at most root p over s. And if I did this right, root p is root log 1 over delta. So this thing should be root p over s is up to a constant the same thing as epsilon over root log 1 over delta, which is the same thing as 1 over root m. Okay? Just by our choices of p, s, and m. So, good. We're done. What we've shown is the p norm is equal to this p norm. And we've just shown that this thing is at most root p over m, or to be a little more suggestive, okay, let's say root p over m plus p over s. Right? Where? You mean over here? Well, we just showed that the p norm of the we just showed 1 over root m, right? Yeah. So I put in that root p. So we got this. So this implies, right, by Markov, the probability that this thingy pi x squared minus 1 is bigger than epsilon, well, that's at most the p norm of this thingy to the p over epsilon to the p. This is Markov. Okay, and I mean, I guess now you're just done, right? So this is at most, well, the sum is at most twice the max. So if you want to think about this, you could say this is at most 2 times the max of root p over m, and then so root p over m, p over s over epsilon. Okay, and if you just do the calculation, and this, I guess, to the p as well. If you just do the calculation, then this thing is at most delta. Okay. For our settings of p, s, and m. So now it's just a matter of proving the claim. Okay. So that's the thing we want to argue about. Okay, so remember, so proof of claim. Remember, Qij is the number of times I and j collide. So let's just fix column I. Remember that columns I and j are independent of each other, right? So column I, he has s non-zeros somewhere. Okay. And then there's column j. And the question is, in these matching locations, does he also have a non-zero? Remember, this column is independent of that column, but these entries are not independent of each other. Okay. So let's write, right, the number of locations here is s, the number of on locations. So let's write y t is equal to, it's an indicator random variable, 1 if column j collides in tth row. By tth row, I mean not actually row number t, but this is row 1, this is row 2, this is row 3, this is row t, or row, et cetera, and 0 otherwise. Okay. This implies that qij is equal to the sum t goes from 1 to s of yt. Okay. So as I mentioned before, if we actually had independence across these entries, this would just be turnoff bound. But the thing is, they're exactly s. So given that some of these match, it changes the probabilities of the future ones. So now what I want to argue is I want to argue that if you look at this random variable and look at any of its moments, okay, the moments are dominated by the case of that they're independent. Okay? So, whatever tailbound you're getting using moments from the independent case automatically hold for this case because the moments are dominated. And as you know from P set 1, what are Chernoff and Bernstein, et cetera, other than moment bounds? Right? So you can apply Bernstein or Chernoff, and you get the same kind of result. Okay. So why is that the case? So moments are dominated by independent case. Moments of this thing. Why is that? Well, let's look at sum over t of yt to the p, and let's look at the expectation of that. Okay? This is going to look like some sum or some subset of the indices, right? You're just going to have lots of monomials. So some sum over all, how many distinct indices did you pick? S goes from 1 to the min of p, and how many are there? S, I guess. The sum of all the powers that you raise them to, d1 up to ds, such that the sum of the d's is equal to p. And then you have the sum over all choices of indices. I1 is less than I2 is less than is less than IS. And then here you have some multinomial coefficient for all the ways to choose indices that have these powers, okay? And then you have the product, expectation of the product of yi q to the dq, where q goes from 1 to s. Okay. The details of what this number are, et cetera, don't really matter. The point is just imagine actually expanding this out to the pth power and looking at it monomial by monomial. Okay. So a generic monomial looks something like this. There's going to be various y's raised to various powers, and some coefficients there from combinatorics. Okay. Now, these y's are indicator random variables. So raising them to powers, let's say all of these are also bigger than 1, right? These are all at least 1. If you raise them to a power bigger than 1, it doesn't do anything. They're either 0 or 1 anyway. So these powers really don't matter. Okay? So in the independent case, what is this expectation in the independent case? First of all, if you look at any particular y, right? What's the expectation of a particular y? Right? So if you just look at one particular entry and ask, what's the probability that this guy is on? It's S over M. Right? Oh, yeah, sorry, I shouldn't have used S again. Let me use L. right? So in the independent case, so let's look at this number, call this number alpha. In the independent case, alpha is S over M to the L. How about in our case? They're not independent, right? The expectation of the product of these yiq's, q goes from 1 to L, well, that's just equal to the expectation of, well, it's the probability that they're all 1, right? For this thing is either going to be 1 or 0, and it's going to be 1 when they're all 1. So this thing is equal to the probability that yi1 is equal to 1 times the probability that yi2 is equal to 1, given that yi1 is equal to 1, times the probability, et cetera, yi3 is equal to 1, given that yi1 equals yi2 equals 1, et cetera. Right? So let's just write what this is. So what is the probability that yi1 is equal to 1? It's S over M. What's this probability? Given that you know that one of them is 1, what's the probability that some other guy is 1? Yeah, S minus 1 over M minus 1. Right? Times S minus 1 over M minus 1 times S minus 2 over M minus 2, et cetera. Each one of these things is less than S over M. This is at most S over M to the L. Okay? So that's pretty much it. So we know now that the moments of this are term by term dominated. Well, the monomials here are term by term dominated by the independent case. All the summands are non-negative, which means the entire expectation is dominated by the independent case. So now the question is just, what are the moments of this thing in the independent case? Right? And that you can get from Bernstein or something. So maybe I'll just put that in the notes. Okay? So there's nothing interesting there. This is really the only interesting thing, is realizing that it's dominated by the independent case. So any questions? That's the analysis. Yeah. Yeah, it tells me that, right, so I had this claim that the p norm of Qij is at most p, and if that were true, I could finish the proof. And then now I just needed that upper bound to hold. Yeah. Yeah. So okay, we're saying why didn't we just have expected S per column? Why did we need exactly S per column? And the reason is actually this very first bullet. Okay. If we had expected, so let me just maybe write this down. Basically, this Bx matrix wouldn't have 0 diagonal otherwise. Okay, so let me what do I want to do? Yeah, let me write it here. If you just expand this thing out, pi xl2 norm squared minus 1, this thing is equal to 1 over s times the sum r goes from 1 to m, sum I from 1 to n, delta ri xi sigma I squared. And this thing is equal to, if you do this out, 1 over s sum r from 1 to, right, so sum I xi squared, sum r from 1 to m, delta ri, plus 1 over s sum r from 1 to m, sum I not equal to j, and then some other stuff. So if you subtract, oh, and I subtract 1. And let me also again subtract 1. Okay? And the point is, because we have exactly s non-zeros per column, this thing is equal to s, which then cancels that, and then this thing cancels that. Okay? If you have expected s, then that's not true anymore, which in our picture basically means this matrix Bx is the wrong matrix. So notice when we were looking at the Frobenius norm squared, where did I go? Yeah, this. When we're looking at the Frobenius norm squared, we only had to sum over I not equal to j, right? And that saved us. Because if we had to sum over the diagonal as well, it always collides with itself, right? And that's no good. Yeah. Okay. So that's Sparse JL. Okay, so I mentioned last time that there are two ways of getting faster JL embedding matrices. One is by sparsifying pi, and the other is by using a structured pi. So now I want to tell you about how to use a structured pi. And the advantages are, here we're getting a runtime, which is like s times. So if you want to actually multiply pi times x, the runtime is something like s times the support size of x. Right? Ideally, you want something that's linear in the support size of x. Right? You want big O of support size of x to do the embedding. You basically just have to read the vector, and then in linear time, you can embed it. But we're getting this multiplication by s, which is not a constant. So this is not linear time. The runtime, so just if you do it with for loops, pi times x can be done in time s times the support size of x. Right? Just because if you write pi as being this matrix, pi 1 is the first row, pi n is the pi 1 is the first column, pi n is the last column, then this implies that pi x is just the sum I goes from 1 to n of xi pi I. Right? So how many terms are in this sum? I mean, the support size of x. You only care about the xi's that are non-zero. And for each I in the support of x, you have to add pi I into your output vector. But pi I only has s non-zero entries. Right? So for each xi in the support, you're spending s time. So the total time is s times the support size. OK. So the other approach that I'm going to tell you about, the fast JL approach, is based on a structured matrix. And it's going to have the property that I can do the embedding in roughly n log n time. Now, if the original vector were sparse, then let's say the original vector sits in n dimensions, but it only has 10 non-zeros, then n log n is terrible. Okay? But if the original vector is dense, then n log n is nearly linear time. Right? So this is a better approach when you have dense vectors. Okay, so let me use this board over here. Any other questions before I show you that? Okay, so actually, the approach I'm going to show you now, historically, this approach was discovered before the sparse approach. So let's see this thing. So this is called what I'm going to show you is called the fast JL transform, usually called the FJLT. Okay. And the reference for that is the original conference paper was in 06, the journal paper was in 09, Eilon and Chazelle. Just because it's slightly easier to analyze, I'm going to analyze a slight variant of what's in their paper, but the ideas are very similar. Okay. So what's their matrix? So pi, according, I'm going to use the letters in their paper. Pi is going to be equal to the product of three matrices, PhD. Okay, because this matrix, this thing was in, I think, Eilon's PhD thesis. So he called it PhD. Okay, so, and I mean, it's sort of, well, other than the P, I don't know about the P, but the other two fit. Okay, so D is going to be a diagonal matrix. Okay, so that's why it's D. So this is a matrix that's n by n. So this is n by n. This is also n by n. And this thing here is m by n. So the total matrix is m by n. D is going to be a diagonal matrix with random signs in the diagonal. H, we just needed to have two properties. The first is that it's an orthogonal matrix. Okay, if you forgot what that means that H transpose H is equal to HH transpose is the identity. And the second property we're going to need is that the max over all ij of hij is O of 1 over root n. So the maximum magnitude of any entry is roughly 1 over root n. We also want that H supports fast matrix vector multiplication. After all, we do want this thing to be fast. Okay, so do people know such an H? The identity is not, it doesn't have the second bullet, that's right. But it does have the other two. Okay, so one such H is the discrete Fourier transform. Okay, so the discrete Fourier transform is orthogonal. Each entry is something like, e to the whatever over root n, e to some complex number over root n. So all the magnitudes are 1 over root n. And you can compute hx using the fast Fourier transform. So that's n log n time. And then P, this is where I'm going to differ a little bit from what's in their paper. P is going to be, for me, just because it makes it easy to analyze today, it's actually going to be a diagonal matrix. That's n by n. I lied a little bit, but you'll see what I mean in a second. And let's say eta 1, eta n 0, 0, where eta I is equal to 1 with probability m over n and 0 otherwise. So kind of P is a matrix that selects out an expectation m of the rows of H. So in expectation, this matrix has m rows. The number of rows is a random variable. That's not really important. I'm just doing it because it'll make my writing down the analysis a little simpler. You could also just sample exactly m rows from H. Okay, that's also fine. Technically, I also need to scale this by square root of n over m to get the right scale. Okay. So that's the matrix. Let me say a little bit about the intuition. Why do you want to do this construction? Okay. So let me use this word. The basic idea is suppose we form an m-dimensional vector y. So y is pi x. And each entry of y is just a random sample of a coordinate of x. Okay, so imagine that we had y, which was just px. Okay, and with the scaling, root n over m. It's not too hard to convince yourself. So let's say that, it's not too hard to convince yourself that I'm not going to do it. That the expectation of yi squared is equal to, x2 norm squared over m, which is 1 over m, which implies that the expectation of y L2 norm squared is 1. Okay? So this is great in the sense that the expectation is right. Okay? If we sample coordinates, then we get the right expectation. What do we actually want from JL? we want that the probability that you deviate from the expectation is really small. Right? The probability to deviate by epsilon is really small. So what's the problem here? Yeah, the variance is too high, right? And why is the variance too high? Well, what if the vector x had a 1 in one location and zeros everywhere else? Right? Then you're going to, in order to even see that one, you're going to need to sample n coordinates in expectation. So m is going to be like n to even see that one. Okay. So that's the only thing really killing us, is the fact that x might be concentrated in very few coordinates. Now, so the intuition here is actually from physics. It's from quantum. So I don't know if people have heard of the Heisenberg uncertainty principle. Maybe you've heard of, even if you don't know what it is, maybe you've heard it in popular culture or anything, or something like this. Okay? And what that thing says, let me not be too precise, but basically what it says is, if you look at, for any vector x, it cannot be the case that both x and hx are concentrated in few coordinates. Okay, that's what it says. Okay, so for example, if you take the vector x, which is 1, 0, 0, 0, 0, and you apply hx, well, now it's perfectly spread. What's h times e1? It's the first column of h. The first column of h is basically 1 over root n everywhere. And if you're 1 over root n everywhere, sampling is perfect. In one sample, there's no variance. Okay. Okay, so unfortunately, you might have this opposite effect. What if the original vector was actually perfectly spread? So now you're saying, okay, instead of using px, I'm going to use phx. H is going to spread it around, and then sampling works. But if the original vector is perfectly well spread, h might collapse it to a single point, and then p doesn't work anymore. And even though I said that a vector and its h, and its a vector and its Fourier coefficients can't both be well concentrated in a small mass in a small number of locations, it can happen that they're sort of mediocre concentrated in both. So you can come up with an example of a vector that both it and its Fourier transform are concentrated on something like root n coordinates. There exist such vectors. Okay? So even if you do x or hx, you're still going to need to sample root n coordinates to see any mass. And I don't want to sample root n. Right? What do I want to sample? I want to sample 1 over epsilon squared log 1 over delta. That's my JL bound. Okay? And that's where the D comes in. Okay, so the usual way that, well, the way that Ailon and Chazelle analyzed things is they had a following claim. For any x, let's say x has unit norm. Okay. If you look at this random vector, this random matrix D, so if you look at alpha being random sign vectors, the probability that h dx infinity is bigger than something like some constant times square root log n over delta over n is at most delta. So they have some kind of claim like this, right? So what does it mean to be perfectly well spread? Well, if it has unit norm and it has n coordinates, right? Perfectly well spread means 1 over root n everywhere. So this is saying it'll be almost as good as that. Up to this root log factor, it'll be perfectly well spread. No coordinate will have too much of the mass. And then if you do Bernstein or something, yeah, you can do Bernstein, and then sampling you can analyze sampling, and then you get something. Okay? So after Bernstein, can show m being something like 1 over epsilon squared log 1 over delta log n over delta suffices for failure probability delta. So you're not getting exactly what we like to get for JL, right? There's this extra slop. Right? Usually for JL, we want to get M to be something like that. That extra slop basically comes because there's that. Okay. So what might you do to fix that? Suppose you actually wanted to get the right JL bound. What's something kind of without really thinking much, something that just gives it to you? So now you have a vector. Think about it this way. Y is equal to PhD x, right? And y is now a vector that's too high dimensional, but it has the right norm. So what do you do to y? You do dimensionality direction on y, right? So your final matrix can be pi prime, which is root n over m PhD, and then you also have a matrix G, which can be a Gaussian matrix or your random sign matrix or Sparse JL, whatever. This will be a matrix that actually has JL with the right parameters. And so your final runtime will be basically the runtime. Your final bound will actually be this, because G has the right number of rows. And your runtime will be, well, linear time to apply D, n log n to apply H, linear time to sample. And then now you need to actually apply G to that final vector, but the dimension of that vector is not n anymore. It's this. So the total time is n log n plus the product, let's call this now m prime times m, plus, and m prime is going to be the right thing. M prime is going to be 1 over epsilon log, well, 1 epsilon squared log delta. Or you could use sparse JL and save a factor of epsilon there. Okay. And there have been subsequent works which improve this. Okay. Both change the construction a little bit and also do the analysis in a very different way. Question? Oh, you mean the newer works? Yeah. So the newer works actually get you n log n. However, so they don't get you. You can always do this at the very end. But suppose I don't want to do this at the very end. Okay? You can view this construction as getting you. You can view this construction as getting you this kind of bound in n log n time. So the one question is just, in n log n time, what's the best bound that I could put here? And the newer constructions, what they give you is log 1 over delta over epsilon squared times polylogarithmic in n. So they don't depend on delta. Here, the unfortunate thing here is you have log squared 1 over delta, basically. Right? And I might not want, there are some applications which we will see in an upcoming topic very soon where delta is actually going to be exponentially small in some parameter. Because you want a union bound over a net of some vectors, you'll set delta to be exponentially small. And then log squared 1 over delta is kind of a disaster. Okay. So kind of those newer results avoid that issue. Actually, maybe the right thing to say is the newer results, one thing is they're less about distributional JL and they're more about, no. Yeah, that's fine. Yeah, what I said is what I meant to say. That's right. So actually, okay, the actual Eilon-Giselle paper, P is not going to be a sampling matrix, but P is actually this like random sparse matrix, very sparse. Okay, like almost a sampling matrix. Like instead of one, a sampling matrix has one non-zero per row. Theirs might have polylog non-zeros per row. So it's like almost a sampling matrix. The kind of the newer analyses, they actually just use a sampling matrix. But the analysis is totally different. They don't go through this claim at all. Okay, they don't. It's not viewed. Actually, it's. I can say one thing right now. I'll say more later about this in future parts of the course. Kind of the way that we're viewing this right now is HD is like a random preconditioner, such that it conditions X nicely with high probability so that P works. Right? That's how we're viewing it. The later analyses do something kind of the opposite. They say that pH, look at pH as being a random matrix, and then they condition on pH having a nice property, namely the restricted isometry property we'll see in compressed sensing later. And then conditioned on pH having this nice property, then they argue that D makes it have the distributional JL property. Okay. So they take a different viewpoint on this thing. That viewpoint was kind of first explored by Ilone and Liberty and really pinned down by Kramer and Ward, and kind of all the subsequent improvements go down that path of arguing that pH has some property, and then you apply D. Yeah. Yeah. Oh, you're saying could I use the wavelet basis? Yeah. So I'm not sure that the wavelet basis has the second bullet property. Yeah, actually, I think. Yeah, I think maybe not. You can use things like the Hadamard matrix. So I can write one such matrix down. So if you don't want to deal with complex numbers at all, this matrix also has those three bullets. So define Hij as 1 over root n, -1 to the I dot j. What do I mean by I dot j? I mean view I as being a number between 0 and n minus 1, where n is a power of 2. Okay? And then now write I in binary. I is a binary vector of length log n. And do this dot product over the finite field with two elements. Right? This is like the parity of I dot j. This matrix also has those three properties. Okay. I mean, the way to see it is that it satisfies, if you look at the n by n version of this matrix, it actually looks something like this. Look at the n over 2 version of that matrix, and just repeat it several times and put a minus version of it here. You can prove that this matrix satisfies this recursive identity, and then you can use that to prove that it's orthogonal, and you can use that, well, it gives an easy kind of recursive algorithm to get n log n time. Yeah. This is called the Hadamard matrix. Okay. And actually, I'll just point something out. Kind of, I guess, I will. So you're taking the notes, so right? So I'll inject something into the notes that has an analysis of this. In fact, the original paper conditioned on this claim occurring, this nice event, and then said that sampling works, and then you get this log n dependence. If you're a little more careful, you can actually replace this n with an m, so that you get an m here. To get that, though, you don't just condition on this claim. You do something you organize the proof a little differently. I'll put that in the notes. But I think this is the easier thing to see conceptually. Okay. So we still have some time. I'm going to say one. So you're already seeing one application of JL in this P set. I'll give you another application right now, and then we're going to start a new topic. So we did streaming, we did dimensionality reduction. We're going to start a new topic. It's again going to be related to both sketching and dimensionality reduction, as you're going to see very soon. Okay, so all these things use similar ideas. I guess JL, we started off doing random sign matrices, which was basically the AMS sketch. And then the count sketch became relevant for Sparse JL. So lots of these things are useful in across different domains. One application that I want to mention right now is high-dimensional approximate nearest neighbor search. Some people usually say approximate nearest neighbor. Okay. So let's say over vectors in RD, and also today we're just going to look at L2 distances. So if you remember your CLRS or undergrad algorithms, well, actually, these days, I think I didn't mention this in 124, but let me just say this. So let's say the usual way to do it is to set up what's called a Voronoi diagram. Oh, actually, let me define the problem. We're given endpoints P, so P1 up to Pn, and they're each d-dimensional. It can be another distance, another metric. It doesn't have to be L2. Today we're going to talk about L2. Okay, and we have to create a data structure to store these n vectors. Okay. Think of this is a static data structural problem for now, meaning that I'm not allowed to insert and delete points. There's just a fixed database. Okay. And a query is Q, or Q here is an RD, should return the point in your database which minimizes the distance P minus Q. Okay. So this kind of thing gets used in a lot of places. For example, image retrieval. Okay, so I mean, L2 might not be the right thing there, but imagine some other metric. So I have some metric which somehow encapsulates when two images are very different. Okay, and I don't know, Facebook. Okay, and I have lots of images of people, and I store it in a database. That's the dynamic problem because my database keeps changing. But let's ignore that for a second. And a query comes along, which is someone uploads a new album, and Facebook wants to auto-tag it. Okay, so they're going to take that image that you uploaded. They're going to do some image recognition. They're going to do some face recognition algorithm to find faces inside that image, and then they're going to query. I'm not claiming that this is exactly how Facebook does it. This is just a plausible hypothesis. Okay, so I'm going to query my database of faces and find the one that's closest to the image that you just uploaded, and then I'll suggest an auto tag. Okay, or for example, maybe I'm the NSA and I want to identify someone in a photo after some terrorist incident. Okay, so you can imagine such things getting used in various contexts. Another one, they don't use L2, but I have a bunch of documents. Document retrieval is yet another one. Okay.
Where does the approximation come from?
Oh yeah, sorry. This, as I've written it, this is the exact nearest neighbor problem. Okay. Approximate nearest neighbor says return a point P in capital P such that P minus Q is at most some constant C times the min over P prime and P minus Q. And C is my approximation factor. So think of C as potentially 1 plus epsilon. But it could be some other constant as well. Okay? I'm willing to have someone who's within a factor 2 of the distance of the actual nearest neighbor. Okay. Good. So one way to solve this problem, so exact near neighbor solution, you can use what's called Voronoi diagrams. And then planar point location. So what's a Voronoi diagram? Let's imagine that D, the dimension is 2. Okay. I have a bunch of points. And they live in R2. They divide up the plane into regions, where let me try and draw the bisectors. So let's say this is kind of everything on this side of the line is closer to him than to him, right? And then each pair has their own bisectors. And then this one said this. I'm very bad at drawing. Okay, so I think what I can say now is everyone in this region has this guy as their nearest neighbor. Then there's also this. Something like that. Everyone who's like here. I think has this guy as their nearest neighbor. And you can keep filling this thing in, and you get a division of the plane into regions such that anyone in this region has this guy as his nearest neighbor, et cetera. Everyone in this region has this guy as his nearest neighbor, et cetera. Okay, so construct the Voronoi diagram. In 2 dimensions, you can do that quickly in nearly linear time, like n log n. And the second thing is planar point location. Now that I have this planar subdivision, I get a query, and I want to figure out which region does it actually belong to. Okay, there are fast algorithms that do that too, like log n time. Okay, so these are kind of classic computational geometry problems that people have efficient algorithms for when D is equal to 2. Okay, there's a problem. It's called the curse of dimensionality. Well, this is one manifestation of the curse of dimensionality, which is that in D dimensions, Voronoi diagram can have complexity n to the theta of D. Something like n to the d over 2. So just to describe all the regions will take you n to the d over 2 space to describe what they are. Okay. So already your space is, what's the space to actually store the data? It's nd. They're n vectors, they're each d-dimensional. But it's like n to the d over 2 to actually store this Voronoi diagram. Okay? And that's just, if you're working with large data sets, you can forget that. Okay? Imagine that you're dealing with images that are 1,000 by 1,000 pixels, right? So D is 1,000,000. D over 2 is 500,000. Okay, great. Your space is n to the 500,000. It doesn't make any sense. Okay. Even if you used, well, yeah. So let me just put it like that. That's right. That's right. Of course, the other thing you can do is just, one way to solve the problem is just store the points exactly. Store the points just kind of in a list. And then when you do a query, just query over the entire list. That space is great, but then the query time is ND. The query time sucks. Okay. So here's where approximate nearest neighbor comes to save the day. Let me start writing over there. Okay, so this approximate nearest neighbor, it reduces to another problem that I'll call C near neighbor. This reduction, you can find this reduction, for example, in the paper Harpaled, Indik, and Motwani in 2012. So actually, kind of the original reduction, there was a paper by Indik and Motwani in 98. They had some complicated one. Harpaled later had a simpler one, and then the journal version has, I think, an even simpler one. Okay, this reduction. And what is C near neighbor? If there exists a P, okay, so let's call it actually CR near neighbor. If there exists a P in the point set such that P minus Q is at most R, then return P prime in P such that P prime minus Q is less than or equal to CR. If no such P, you can fail. Output fail. Okay. So kind of the easy reduction from approximate nearest neighbor to CR near neighbor is basically just binary search on R. Okay. So just try some value of R. If nothing came up, well, double R. If it still doesn't work, double R again, et cetera, and do a binary search kind of thing. Kind of the only issue, in reality, you can probably get away with that depending on kind of the aspect ratio of your data set. The issue with that is kind of the number of iterations of your binary search doesn't depend on n. It depends on something like aspect ratio of the point set, something like that. The reduction in this paper avoids that, and it actually gives you some kind of binary search-like reduction where the number of iterations is only log n or log squared n or something like that. So I'm not going to talk about that. Let's just pretend that you had that, imagine just doing a binary search and paying log aspect ratio or something. So then the question is, how do you solve this problem? And there are a couple, let's say there are a couple flavors of this. And we'll just talk about one in the last few minutes just because it follows pretty simply from what we've done with JL. So CR near neighbor. So let me write here space time, and when I say time, I mean the query time, and then say reference. Okay. So space, let's say dn, just to store the data, plus something like n to the o of 1 over epsilon squared. Okay. You can get query time to be something like, I think d plus, you can certainly get this, roughly. Or if I, just to be safe, let me say polynomial in that. So this is Kushilevitz, Ostrovsky, and Rabbani. Ostrovsky and Rabbani, 98. Also Indik and Motwani, 98. There are a few, there's some slight difference, there's some difference between these two. I'm not going to get into it here. Then there's kind of the other approach, which is the LSH approach. You'll see what I mean in a second. So here, the space is going to be something like dn plus n to the 1 plus rho of c. So here, by the way, in this row, c is equal to 1 plus epsilon. Okay. Yeah, so good. And your query time, maybe I should divide this from what was before. So we're now in a new age. So everything below this line is going to have space, which is this, and query time, which is something like this. And now the question is, what's rho, as you said? So one thing you can get is rho being something like 1 over c. Okay. So this is Indik Motwani 98. You can also get rho being something like, this is rho of c. You can get rho of c being something like 1 over c squared plus little o of 1. This is Andoni and Indik 2006. Right? Imagine now c is like a big constant. It's not 1 plus epsilon. C is like 10 now. Okay? So this is better, right? This is 1 over 10 squared is 1 over 100. So my query time is n to the 1 over 100 as opposed to n to the 1 over 10. So this is better. You can also get something like rho being 7/8 c squared plus o of 1 over c cubed. This is due to Andoni, Indik, Wynn, and Rasenstein. I believe this was 2014. And then kind of the latest of these is rho being 1 over t 2c squared minus 1 plus a little o of 1. And this is due to Wynn and Rasenstein. Okay. The last thing I want to put, the space is something like roughly, maybe up to logs, I'm not sure, dn. So it's actually linear space. And rho is something like 2.06 over c, something like that. This is due to Pandigrahi. And kind of all of these fit into something called LSH, which is locality sensitive hashing. It's kind of a paradigm for designing these kinds of things. By the way, if anyone wants to do an implementation project, I mean, some of these are very new, like this one over here and this one. LSH is actually something that people use. There's a package online on Andoni's website. I think it's called E2LSH, maybe. And people who do things like image retrieval, et cetera, actually download it and use it, and occasionally email him with questions. So they're asking questions because they're using it, right? So if you actually, if you wanted a good implementation project, one thing is maybe try one of these theoretically better ones and see and compare it with this one, which is implemented. And if you did a good job implementing that package, people might actually start using it. So good. So today, I'm actually, in the time I have left, I'm just going to cover this one, the first row. Yeah.
Just curious, why does it call locality specification?
So the data structure uses as a primitive what's called locality sensitive hash functions. And the basic idea behind, so what's the idea behind such a family of hash functions? You want a family of hash functions such that if two vectors are close to each other, it's likely that they'll hash to the same place. And if they're far from each other, then it's not likely that they'll hash to the same place. Okay? And then you can use these hash functions to design a data structure, to design data structures that kind of help you find close vectors. So here you want things to collide if they're close. So that's locality sensitive hashing. Yeah. Oh, with additive error, I'm not so sure about that. Because, I mean, one thing that makes me a little worried is if I scale all the points, all the distances get scaled, right? So what if I scale all the points to something really big? Wait, sorry, say it again? Yeah, exactly. If I scale the distance to something huge, then additive starts going to 0, right? So as relative to the actual distance. So. Okay, so let me just show you that first bullet. And I'll show you the version from Indic and Mutwani. Okay. So actually, what I'm going to show you is something like n to the O of, this is what's in their paper, log 1 over epsilon squared space. Okay, dn plus that. First, we'll get space something like dn plus n times O of 1 over epsilon to the d space. Okay. Why does achieving this space imply that you can achieve that space? Notice there's no d here. I made it over here. This is JL, right? Basically what I'm going to do is in pre-processing, I'm going to pick a random JL map and just hit every single vector with it. Then d becomes log n over epsilon squared. And 1 over epsilon to the log n over epsilon squared, if you just rewrite things, is this. Okay. So this is a bit, I think this is why LSH has taken off more than this. This is actually quite a large amount of space. It's nice from the theory point of view. For any fixed epsilon, it's poly n. But n to the 1 over epsilon squared is actually pretty bad, right? Whereas these things are actually taking nearly linear space and pretty good query. OK, so we just want to achieve this. And how are we going to do it? Pretend R is 1. OK? The case for general R is basically the same thing. Okay? What we're going to do is impose uniform epsilon over root d grid on RD. Okay, I just mean like, yeah, a grid where all the side lengths are epsilon over root d. Why did I choose epsilon over root d? Notice that the diameter of any grid cell is at most epsilon, right? If you have a box that's epsilon over root d in d dimensions, no length is longer. Like the diagonal is length epsilon. So this grid cell has length epsilon in L2. Okay. Now, for each pi and p, let bi be the L2 ball around pi of radius 1. Let bi bar be the set of grid cells that bi intersects. What we're going to do is we're just going to store b bar, which is the union over all bi bars, I goes from 1 to n, in a hash table. The key in the hash table is the grid cell ID, like telling me which grid cell it is, and the value is I, which point had a ball that intersected this thing. And then now, how do I answer a query? Okay. Well, if I get a query vector, it's pretty easy to tell what grid cell it lands in, right? Okay, just divide all the coordinates by epsilon over root d, and that'll tell you which grid cell you're in. And then just check. Right? So we're doing C1 near neighbor, right? So the assumption is this point is within 1 of someone. If he's within 1 of someone, then his grid cell intersected that guy's ball. And then we're going to output that guy. But it might be that, here's our grid. It might be that he intersected our grid, but we're not actually in the ball. But this grid cell has diameter at most epsilon. So our distance to the ball, because someone in that grid cell intersected the ball, our distance to the ball is at most 1 plus epsilon. So this solves the c equals 1 plus epsilon in your neighbor. Okay? So querying is very fast. Just look up in a hash table. The only question is, what's the space? Okay. So kind of notice that if you blew up this ball, so the question is just how many grid cells can this guy touch? Notice that if you blew up this ball to not be radius 1, but radius 1 plus epsilon, it would contain every grid cell that it intersected. Right? So the number of grid cells is at most intersected, is at most the volume of a radius 1 plus epsilon ball divided by the volume of a grid cell. Right? Call this number R. You can look up in a book what's the volume of a ball, a unit L2 ball in d dimensions of a sphere. It's some number, and that number happens to behave something like r to the d times 2 to the O of d over root d to the d. Okay, I'm just going to use that fact. I just want to say that because what I want on the numerator is some shape that actually contains. Oh, I see. Wait, sorry, say it again.
I mean, it's how many grid cells can they want to intersect, right?
Yeah. right? So the point, is this shape right here contains all the grid cells. But if it contains all the grid cells, its volume has to be bigger than the volume of the union of all the grid cells, right? So how many grid cells can it take? Can it actually contain the ratio, right? So this is this. The bottom, the volume of a grid cell, it's just a box. It's epsilon over root d to the root d. This cancels that. R is 1 plus epsilon. So at the end of the day, this is O of 1 over epsilon to the d. Well, so let's say this is at most C over epsilon to the d. For some constant C. So actually, I shouldn't have said 1 over epsilon to the d. I should have said C over epsilon to the d. So that's it. Okay. Any questions? You also have to take into account the time to actually, because when you get a query, remember if we're doing JL, you have to actually apply the JL map to the query before you search in the database. So you also have to add in for the query time the time to do the JL map. But if you do fast JL or something, that's nearly linear time in the dimension. Okay? So